Hello students, welcome back. Now let's go to section 3 of this problem set, graph problems. All these problems are associated to this graph. And that graph is a graph of y equals f of x, lowercase f. And we have to answer the questions about capital F of x and capital G of x, both of which are given in terms of the definite integral. Okay, let's answer the first question. First question is about the right function, capital F. Determine the intervals of increase and decrease of the function capital F of x, and also find all critical numbers of capital F of x, or equivalently speaking, the x-coordinate of the critical point of f of x, and determine their nature. Local maximum, local minimum, or neither. Okay, how does it work? The key is to recognize this. Capital F is an antiderivative of small f. That's the nature of fundamental theorem. Actually, fundamental theorem of calculus has many aspects, and this is one of many aspects. Antiderivative function. So definite integral is basically antiderivative computation. If you take the derivative of antiderivative, we get the original function back, so we have the small f of x back. In other words, this graph here is the graph of the derivative function. And if you know the sign of the derivative function, we can tell the increasing, decreasing of the original function. That's basically what we're going to do, because this is basically the derivative. And here we go. Let's see. Yeah, okay, let me copy and paste this down below. Okay, here we go. This is 0, -1, -2, -3, -4, -5. Okay, -5, that's where we have crossing. And -1, we have crossing. And +2, we have crossing. And +4, we have crossing. And then less than -5, the derivative is negative, so original function is decreasing. From -5 to -1, above the x-axis, so the derivative is positive, so the original function is increasing. From -1 to 2, the derivative function here goes below the x-axis, so it's negative, so the original function is decreasing. Positive, so increasing. Negative, decreasing. So we have this diagram which completely determine intervals of increase, decrease, critical numbers, and their nature. I don't think you have to re-express all the intervals separately unless MyMATLAB or WebAssign explicitly requires you to. Okay, alright, that completes the first problem. Now let's go to the second problem. This is going to be a little bit harder because G is a little bit harder, just a little bit harder. Now we have 0 versus 2. Will that make any difference? No. X up here versus X down here, will that make difference? Yes, it will. How? Well, please remember this. If I flip the, oh, excuse me, what did I do? Wrong key. If I flip the order of the integration, it's the same as putting negative sign. You see the fundamental theorem? Plug in the top, plug in the bottom, and subtract one from the other. Now, if you switch top and bottom, I'm switching the order of the subtraction, which is equivalent to taking a negative. I hope everybody remembers. And that's what we're going to apply here. You see? Flip order set negative, so capital G prime is negative f of x. Consequently, capital G prime is negative capital F prime. What does it say? When capital F is increasing, capital G is decreasing because it's precisely the opposite. And then capital F is decreasing and capital G is increasing. Basically, we have this diagram. So precisely the opposite behavior as before. So if you see this negative, then this is easy, but it's not always that easy. A is full problem and B will be just half problem. It's a little bit trickier, but after that trick part, there's no substance, so only half a problem. All right, let's go to C. Estimate the values f of 2 and g of 0. Now, this is pretty much standard. Difficult, yes, but standard. Plug in x equal to 2, then we are talking about integral from 0 to 2. Integral from 0 to 2. And how do I get integral from 0 to 2? Well, we got the shaded part, and then we have to estimate the area, or more precisely speaking, the signed area. Similarly, if I plug in x equal to 0 to g, you're going to get actually the same integral, 0 to 2. Again, we are talking about the same integral, so same shading. So, shade from 0 to 2. Here, right here. Let me show you this part. And then now your job is to estimate the area of this part. And I kind of estimated as actually a little bit less than -2. You see, some part missing here, and then some part added, about push. Some part missing here, some part added there, but added part is a little bit bigger. So compared with this part, the missing part from these rectangles are a little bit smaller. So this geometric area is going to be a little bit larger than 2. So 2 point something, but below the x-axis, -2 point something. And if you do precise computation, it'll turn out to be about -2.25 something, actually. But I never gave you the algebraic expression of this function, so you can never find out precisely. You can do the estimation though, and anything that is reasonable, I would have given you full credit. This kind of problem, the estimation of the area for the definite integral with these grids, those are standard problems. Is it super important? Well, compared with some other kind of integral problems like these, or those, comparatively speaking, no, but still, it's a standard problem. Now, let's go to problem D. Sorry about that. The labeling is incorrect. D. Determine the intervals of concavity. Okay, we talked about increase and decrease when the derivative function is given. How about concavity and inflection points? Well, we already saw the key idea. Capital F prime is small f. Yeah. So this is a derivative function basically, and derivative increases, that is from here to there, concave up. Derivative goes down, decreases, then concave down, and the derivative goes up, concave up, derivative goes down, concave down. I hope everybody remembers that, and that's it. F is going up, down, like this, and consequently, capital F is concave up, down, precisely associated in the following fashion. So, this completely determines the intervals of concavity, concave up here, concave down here, concave up here, concave down here, and the x-coordinates of all inflection points. So I'll regard this diagram as the full answer, full complete answer. Now, as for the second problem here, remember the same thing. Capital G and capital F are related as a negative sign, basically. You see, capital G prime is negative F, which is negative capital F prime. So the property of capital G and capital F are precisely opposite. One is concave up, the other is concave down, and vice versa. So the derivative is going up, then concave down. Derivative is going down, concave up, kind of like that. So down, up, precisely the opposite of capital F. Again, if you see this association, G and F behave precisely the opposite, then it's an easy problem. But if you don't get over that initial hump, then it's impossible to handle. So in this kind of top-heavy problem, I cannot put full credit, so half the problem. As a matter of fact, these half the problems are considered as extra credit. And finally, here's a problem that is kind of super hard, and if this had been real exam problem, I wouldn't have written this kind of problem. Well, it's a practice exam problem, so hey, what the heck, I've inserted those kind of problems. Estimate the values of capital F double prime of 2 and capital G double prime of 0. And what is capital F double prime? The second derivative. Well, this small f is the derivative already. So second derivative of capital F will be the first derivative of small f, basically. So take the derivative, and that's small f. Second derivative is f prime. So at x equals to 2, I'm going to find out, or I'm going to estimate the slope. And get a ruler or something like that, and then draw a certain tangent line, and then estimate about 2. That's the best I could do. Looks like maybe a little bit bigger than 2, because in this picture, I used actually precise algebraic expression. You see, there is an algebraic expression hidden in my program here somewhere. Yeah, there is an algebraic expression here. So for me, it is possible to find that precise value, but I didn't give you that, so that's not something you can actually find out. Okay, how about capital G prime? Excuse me, sign mistake here. Okay, all right, now that looks good. Capital G prime is negative f. So capital G double prime is negative f prime. So we have to estimate the derivative evaluated x equal to 0. And around here, it looks like about negative 1. So negative, about positive 1, approximately speaking, of course. But then again, this kind of problem is highly unusual. So if this had been a real exam problem, I probably wouldn't have written this kind of problem. Or if I did, it's an extra credit. Actually, there already are many other extra credit problems, so that probably is not a wise problem. But what the heck, this is a practice exam problem.